Welcome everyone to my talk, Do You Follow What I'm Explaining? A Practitioner's Guide to Opening the AI Black Box for Humans. As mentioned, I'm Kilian. I'm speaking to you from beautiful Hamburg, Germany, up in the north of Germany. And while I'm trained as a physicist, I do have a PhD on the design of human AI interactions with explainable AI. And I currently work as the co-founder of an early stage startup called Inlinity, where we use explainable AI to build tools to enable human agency in an AI-driven world. Everything I'm going to talk about and a lot of further information on background material and also these slides, you will be able to find on GitHub. I'm at Ionic Solutions there. The slides are not yet uploaded, but I will upload them after the talk. And I will also show the link before we conclude in case you didn't have time to jot it down just yet. In this talk, what I want to speak about is explaining AI systems to lay users or to users that are not data scientists or ML engineers. And very briefly, what this looks like is that we do have what I would like to call an AI system, which has an input. Then there's some sort of model, might be a machine learning model, could also be a different algorithm. And then we have a system output. And now you have some sort of an audience, maybe users of an app that you're building or of an internal tool you're developing that are wondering and asking you lots of questions. So why did this mysterious system map a certain input to a certain output? This is what this talk is about. I've structured it into 4 parts and 1 example at the end, where we will look at a practical example of how you could actually implement this in practice. Because we only have 30 minutes today, let's jump right in. In the first part, I would like to talk about 3 truths about AI that I think are very important to keep in mind when explaining AI systems to others. And the first truth is that there are no true black boxes in AI. And I know that this might sound a bit controversial, and if you're consuming a lot of media or participate in the occasional LinkedIn discussion on that topic, you might be led to believe that there's something very mysterious, intransparent about how especially large deep learning systems behave or are built up. And I would argue that actually we do not, at least not in that sense, have a transparency issue in AI. But at the end of the day, in my mind, it's all maths and bit flipping, right? So it's human-made structures. And for example, compared to trying to understand the human brain, where it's really difficult to measure something and we don't know a lot about the details, right? And we certainly do not have the full picture if we're running machine learning systems, even like huge transformer models. In principle, we can have a look at all these CPU, GPU instructions that are calculated. We can look at the memory at every point in time that we want to. And this is a huge advantage also when we're trying to explain what's going on there. On the other hand, though, almost everything that you have ever created in terms of software, doesn't even need to be AI, will be a black box to your users. That's the second truth, which also makes it challenging because even if you have a very simple algorithm, a very simple model, you might just be adding a couple of numbers. From your user's point of view, even the most simple of models will be very opaque when viewed from the outside. And you will probably all know this. You're interacting with some piece of software. You're typing something in and you get a certain response and you wonder why that actually occurred. And so if we're talking about black boxes or black box AI systems for the sake of this talk, also if you think about the title of this talk, I'm talking about this kind of system. So there's nothing inherently black box, but it's something which seems to be a black box to your users. And finally, the third truth in the first part is that your users don't really care about your model. And I think this is one of the first things that many data scientists, when they start to try to explain and generate explanations for the AI systems for some other groups of stakeholders, where they are misled, is that they, of course, do care about your model. If you're a data scientist and you're training your machine learning image classifier, for example, and it's consistently getting certain samples wrong, you might go and use an explainable AI or interpretable machine learning method to really dig into the details. If you're a researcher, you might try to use these methods to figure out whether there's a tweak you can do to your algorithmic structure of your models to make it even better, or to understand why certain patterns do work and certain patterns do not. But your users don't care. They don't want to know what the algorithmic structure is. They don't care about all the fancy calculations that you do. What they care about is the decision or the recommendation or the prediction that your model effects. And so when you're asking for explanations, this is the level which you need to explain on, and we'll return to this in one of the later parts. With that said, with these three truths under our belt, I would like to give you the first definition, or it's more like a working definition on the kind of subfield of explainable AI I'll be speaking about today, which I like to call user-centric explainable AI. And that's the field of research and practice, if you will, that aims to enable humans to manage the complexity of AI systems by generating explanations for their outputs or their internal workings. And naturally, this already leads us into part two, which leads us to the question, what actually is an explanation? What are we talking about when we say that we are explaining something to someone? And the first thing to realize here is that explaining is inherently a social activity. And you can see this with a little experiment that I would like to conduct with you right now. Unfortunately, we cannot talk to each other, but you can just imagine in your mind what you would say to me when I ask you, why are you here? Why are you sitting in front of your computer somewhere on this planet listening to me talk about explainable AI? And if you've done this, the chances are really high that you've come up with a sentence like, oh, I skimmed the program this morning. This sounded really interesting. Or I actually do have a project at work or at school where I'm looking into explainability, so I wanted to learn more, right? And so you picked you were very quick to come up with an explanation of why you were here that you could potentially say to me. But on the other hand, probably no one of you in the audience thought or said something like, well, I woke up this morning, or a couple of decades ago, I was born, or something like this, which is also a very important part why you actually ended up here in this session, or why you might be watching this later on YouTube or something. But you wouldn't say this as an explanation. And even though we are from very different cultural backgrounds, presumably, and we don't really know each other, you were able to come up with an explanation that I would find very satisfying, that I would accept as an explanation. And as you can, so you can see that it's like really an interaction between two people, and context matters a whole lot. Also, what's important to keep in mind, and that's also a trap that you can fall into as a data scientist, and that I fell into myself at one point as well, is that you try to explain the entire causality chain when explaining AI systems. But when you think about how you explain from human to human, you never start at, I don't know, the Big Bang, and then at some point matter formed, and then the solar system formed, and then planet Earth appeared, and then life appeared, and at some point you were born, right? That's all part of most things that you do in life somehow relate back to something like the Big Bang, but you would never put this in an explanation. And that's also true when explaining AI systems. People do not want to know everything, but what they're looking for is an explanation. And an explanation, when viewed from that angle, is essentially a skill. It's an art, maybe, of selecting the proper kind of causes from this almost infinite causality chain, and from all these little steps and calculations that maybe your AI system is doing, to select the ones that comprise what a human would accept as an explanation. And to make this a little bit less meta and more practical, let's look at another definition. And this is something which I took from the 4 Principles of Explainable Artificial Intelligence. It's a paper by NIST, the National Institute of Standards and Technology. It was published about, I think, 14 months ago. And it's a very practical framework for thinking about these kind of things. And they say that an explanation is something which delivers or contains evidence or reasons for outputs and or processes. That's still quite vague, but it's very practical, because we're no longer talking about explaining or like giving a full list of causes, or being able to deterministically describe something in its full complexity, but we're looking for providing evidence, for providing reasons, but it doesn't need to be exhaustive. And so, moving on into part 3, we've discovered that we kind of have an understanding of what an explanation is, what explaining is about. And let's look at what's actually a good explanation, right? So we want to produce something which works as an explanation, which people will accept. And again, it's always a bit of a disappointment on the first slide of these parts, and quite a daunting task, because the quality and usefulness of explanations are two very highly subjective qualities or properties of explanations. And you can see this, or you will have experienced this throughout your life. You come up with a good explanation for something, or you tell a certain story a certain way to a number of people, and it works quite well. And then you tell it to your grandparents, or you tell it to a toddler, or you're in a different situation, in a different context, and it no longer works. And some people, even though 90% of people will agree that something is a good explanation, you will always find that one person that doesn't agree that it is a good explanation. And that's fine. It actually also makes explaining things a bit easier, because the bar is not as high. Whereas in machine learning, you might be used to these 90+% accuracy numbers in a lot of tasks, even 99% accuracy numbers in a lot of tasks. That's really not the case in explainability. So if you can produce something which the majority of your audience finds useful, finds to be of high quality and likes, that's usually a very good result already. And the second consequence of that fact is that you cannot capture these concepts with simple metrics. A lot of people try to come up with metrics for the explainability, or to measure how comprehensive an explanation is, how realistic it is, how good it is. And I would argue that all of these attempts are bound to fail, because there's so much complexity going on, so much additional context information that goes into crafting a good explanation, that just by coming up with a number of equations, a number of measures or metrics to then benchmark explanations with, that's probably not going to work. And that's very similar actually to what we see a lot in natural language processing, for example, in text summarization, or in question answering, or in text generation. It's really, really difficult to come up even with what I would like to call proxy measures. So something which approximates the quality of the text as it is perceived by humans. And also there we run into this issue all the time. And to give you some insight into what a lot of people think are qualities of good explanations and why it's not so easy, consider the statement, which you can find a lot, especially in the academic literature on explainability, where there's the sentiment that short explanations are better, and they're always better, and you should try to be as concise as possible, and not create too lengthy explanations. And at first sight, seems to make a lot of sense, right? It's quite obvious. Nobody wants to read really long answers or explanations. But on the other hand, if you've ever tried to put very short explanations in front of humans, you might have noticed that it's not that simple. It doesn't seem to be the case, at least not always. And so we don't really know whether that's true or not. But I would argue that it's definitely not always true. And to give you a little bit of insight into one study that I ran during my PhD, I promise these are the only two plots with data in here. What we did essentially is to give people two explanations for the very same outcome that an AI system produced, and then ask them to pick one of them, the one they preferred in that situation. That's a standard experiment setup in explainable AI. And we also had some way to measure the length. So we used essentially the number of features, of input features that an explanation invoked in order to explain the outcome. And then we asked them to pick one of the two, and we also asked them whether the explanation is longer or shorter. And you can see that this measure that we came up with correlates quite well with perception. Of course, it's much easier with length than, for example, with something like realism. It's almost impossible to come up with a measure for realism. But you can see that this kind of works. So if it's really longer, then people also perceive it as longer. And if it's shorter, then people also perceive it as shorter. So that's fine. That's very consistent. And then if you look at the data, you see that in 60% of cases, users preferred explanations. And not just explanations that were longer, but actually they preferred them because they were longer. So they explicitly said, I like this explanation more because it's longer. Of course, there's a lot more details to this than you can see on this slide. But at the end of the day, the conclusion should be that beware of simple metrics, and beware of statements like shorter explanations are better. You really need to figure this out. in the situation that you're working in. But again, we'll return to the paper by NIST, the 4 principles of explainable AI, to again get some more practical things to work with, and something which is maybe better than saying something is useful or of high quality. The first one, the first property of explanations that they carved out is the explanation's accuracy, which means that the explanation correctly reflects the reasons for generating the AI system's output, and or accurately reflects its internal processes. And that's something which is very technical. So this is something which you can, for most explanations and explanation methods at least, that you can assess without even ever asking a human, because you can check whether what your explainability algorithm outputs matches what the model is doing on a more technical level. And so we'll not go into more detail on this here. But the second property is what we continue to work with, is the meaningfulness, which means that the provided explanations are understandable to the intended consumers. And this is something which is very important and is quite often overlooked, especially when you come from this technical accuracy perspective. And then all of a sudden you start to show your explanations to some others, because it's also very easy to not only have something which is meaningless, but it's also very easy to generate explanations that are misleading. And there are some nice studies which I linked on the GitHub page that accompanies this talk, where you can see that even data science professionals, if you, for example, show them bar charts of feature importance analyses or something, that they can be very easily misled, accidentally, but also intentionally. And moving on into part 4, I think we all agree that we want to generate explanations that are meaningful, but how do we do this? And the most important part, at least from my point of view, to consider here is that from the user's point of view, there's not just one stage of pre and post processing that you're used to as a data scientist, but there are actually 2 stages of pre and post processing. And let me explain this. So what you are usually looking at as a data scientist is the AI system that we also saw in the beginning. So you have your input, you do some pre-processing, and then you take whatever the model outputs, and and then you do some post-processing and convert it into something which you then send to your downstream consumers. We can take the example of an image classifier. So you have this image of a cat, which is fed into the system. Then the pre-processing usually looks like something that's depicted here. So you will resize the image, you will maybe make it square, you will have to change something about the color channels, perhaps. And then you have an image classification model in this case, and what this outputs is a vector of the different class likelihoods. And then in post-processing, you determine which is the most likely class, and also what the label for that class is, and then you look up that label, and then you output a string. And this is the level on which you can assess, for example, the technical accuracy of an explanation, and which you are used to evaluating models on. But actually, from your user's perspective, already an image of a cat is something which is highly pre-processed, because nobody, no human, at least that I know, conceives the world in 3 or 4-dimensional tensors with lots of individual pixel values in them. But we see an object, we see an animal. And also, if I read the word a cat, it's much more than just a string. It's much more than a number of UTF-8 characters in some byte encoding, but it's actually something which invokes some sort of emotion. And maybe with a cat, it's quite universal what people perceive. But if you think about a more complex setting, then it's not too difficult to imagine that people might be very easily misled, also just simply by the statements or the visualizations that your explainability system then outputs. And so if you want to evaluate meaningfulness, you always need to do this in your user's world. And it's very important to understand the context that they're working in. Yeah, finally, and I think that kind of follows from that, is that only your users know what's meaningful. And the emphasis should be on the only. There's no way to have a shortcut here. There's no way to engineer your way around this. There's no way to guess what your users will think is meaningful. But the only way to figure this out is to ask them. You can do this directly, or you can do this indirectly by observing their behavior. But if you don't do this, there's no way of knowing this. Yeah. So also with regards to time, let's move into an example, and we will try in the last 5 or 6 minutes to generate meaningful explanations for real estate price predictions. So the scenario is as follows. Imagine you're on a real estate website, and there you have the opportunity to enter data about a house. Might be your house that you're trying to sell, might be a house that you're looking to buy. And in any case, this data is fed into an AI system, some pre-processing going on, as we've just seen. And then there's a pricing model that estimates what the price for this house could be, and what the system believes that you could get for if you put it for sale. And now you have users that are wondering why a certain price estimate was given. So why is my house worth X? And if we now start to understand what the users are actually asking, so that do they want to see the pricing model? I mean, presumably you don't want to give the pricing model to them, but also you will know if you've ever worked in price estimation, especially in real estate, that this is very, very complex. There are so many factors, like, for example, the reputation of a neighborhood, very difficult to put into numbers. This is why machine learning is so great, because you can just learn this from historical data. But if you then dig a bit deeper, or you observe how, for example, people talk to their real estate agents or talk to each other about house prices, what they're really asking is, why is my house worth X instead of being worth a different amount? So why is my house more expensive than my neighbor's house? Why was my friend able to buy a house much cheaper than the price that is offered to me now? And even if they don't explicitly ask the second part of the question, that's what they usually do when they ask, why is something worth X? And that's something we can answer as data scientists, right? So we just need to find a data point for which the pricing model that we use predicts a higher price. Let's say we're going for this direction. And then you will figure out that there are indeed algorithms which can do this, which are called counterfactual explanations. And the idea is that we have this one data point, which is marked as X, for which the model predicts a certain price. And then in order to obtain a different price Y, we just need to move that data point to a different part of the input space, and slowly optimize our way towards there, where the model outputs a different price Y. You can already tell there are essentially infinitely many possible locations we could move this point to, and most of them will not make up a good explanation, because your model knows how to predict prices. And for example, one way to increase the price of a house is to just have more rooms to it, for example, and then you will just add more rooms, you will get a higher price, but that's really not a feasible house. It's not meaningful, it's completely unsuitable. Or you could just add more stories or something like this, or move it to the suburb of a big city. That might be feasible in some sense. People might like that, but usually it's very confusing. You would much rather have a house which could actually sit in the same location, and maybe has like an upgraded heating system. And so what we need to do is we need to find a data point for which the pricing model predicts a higher price. That is also perceived as realistic and typical. And that's something we can do. I'm not going to go into detail here. We just add a number more terms and boundary conditions to our counterfactual explanation algorithm. And then the question is, how do we know whether users actually think that they're realistic and typical? And if you've not fallen asleep throughout this talk, you will know that we need to go ask them. And we can actually do this directly. And one trick I can recommend here, or one suggestion I want to make, is to not reinvent the wheel, but to actually use something which are established constructs. And in the example I've given here, we went to communications and media research, and constructs are essentially sets of questions that you can ask to assess whether a certain property is true about something. And so we just took some ideas from different research papers there, used these constructs, and were able to determine what we needed to do in order so that people actually thought something was a realistic and typical house. And then you arrive at something which looks like this, which are, you can, of course, display this in very different forms, but as a sentence, you arrive at something like, okay, everything else being equal about your house, the house would be worth 600K instead of 350. It was built in 2005 instead of 1999, had a living space of 233 square meters instead of 190, and a lot size of 714 instead of 490. And I think this all makes sense. That's a house you've probably seen in your life. it's conceivable that this would that such a house would exist, and the real estate agent would point to such a house in order to explain to you the price estimate of
Sorry,
your house.
hello, Kilian.
Yeah, I'm closing now.
Just want to let you know we have 5 minutes left, and would you like
I
to
know.
take any questions from the audience?
Yes, so let me quickly conclude with a summary, and then happy to take one or two questions. Thank you. Yeah, so you can see my summary slide here. We've talked about explanations, we talked about meaningfulness, we talked about accuracy. And in the last couple of minutes, I walked you through an example of how to actually do this in practice, which starts with understanding the context and the audience, then the selection of an algorithm that can provide the desired answers, and then to evaluate everything for accuracy and meaningfulness. Yeah, and now I'm happy to take a couple of questions. Just want to, again, point you to my GitHub repository as well, and give a quick shout out to the Explainable AI Slack community. You can find all the information how to join on Twitter and also at the GitHub repository. Thank you, and now looking forward to your questions. Okay, so the question is, what kind of explanations were given in the short-long comparison? Could you add a couple of examples to your Git? Yes, I can do that. I have already linked the research papers about that. So essentially, these were explanations, textual explanations, very similar to the example which we've just seen, but for like a plant species app. So you have a smartphone app, and you take a photograph of a leaf, for example, or of some plant, and then the AI system explains to you what kind of tree this leaf belongs to. And this was kind of the setting that we used in order to assess different properties and qualities of explanations. And everything, all the details are in the Git. Yeah. Are there requirements for actionable explanations? Yes, that's a really, really good point. I didn't have the time to go into detail. Yeah, so if you want something to be actionable, then it's not only sufficient that the counterexample is realistic, but you also need to make sure that you can actually go there. I think one easy example to understand is that if you're applying for a job and they tell you that you should or you're applying for a loan, for example, and they tell you that you need to be 20 years older, that doesn't really help you. But if they tell you that you need to accept a higher interest rate, maybe, or a higher security deposit, that's something which you could conceivably do, or to lower your spending. Yeah, and so you always need to understand the context of your users. Sometimes they are looking for something that they can change and act upon, but sometimes it also doesn't matter. Again, it depends on the situation.